Okay, let's talk about an optimized approach. So in the previous example or the previous naive solution, it took theta of the all the bits in the binary representation. But Brian's continuum, which is an optimization of the previous naive solution, only takes time the number of set bits. So as many set bits there are in the binary representation, it's gonna run for that many times. So what is Brian's algorithm? Before we do that, let's look at the basics, the idea behind it. So basically, the initial representation of number 40 is 101,000. You can calculate it, it's gonna be this only, right? It's confirmed. After that, we're gonna remove this one, okay? This one is removed. So we get this number in the first iteration. Don't think about the code implementation, we'll get into it. But let's imagine somehow magically this one is removed and we get this number 10000. After that, in the second iteration, this one is also removed, the last one. So we get 0000. So as many ones are there, the iteration is going to run for as many times. And at the end, we just going to sum up the iterations. There are two iterations, the response is 2. And this is the correct response because as many times the code runs, there are as many ones in that binary representation, right? So let's look at the idea behind it, how this magic is happening. So this magic happens using set bit count. Okay. So set bit count is basically the number of bits which are set in the binary representation. For example, let's take an example again. We have a number, the similar number 101 and 000. It's basically 40, right? This is the binary representation of 40. What we are going to do is we're going to subtract 1 from 40. So it becomes 39. So when it becomes 39, the binary representation of 39 is 1, 0, 0, triple ones. How did I get it? I simply removed this one. I just switched this bit off and turned all the bits after it on. Okay, let me repeat myself. I simply changed or flipped this bit to 0 and all the bits after this to ones. So I get 39 bits representation. You can calculate it. It's gonna be this only. So this is a simpler way. So you have to find the last most left one and remove that and all the bits after that one are going to change to 1. Okay. After that, we simply do an AND operation. We do an AND operation between 40 and 39. So we get 0, 0, 0, 0, 4 zeros, and then a fifth 0, and 1 gives us 1. So this is the AND operation. So you can relate now, right? We get this number. Okay. In this number also we do the similar thing. We again decrement this. So this value is 32, right? N is equals to 32. It's 2 raised to power 2 raised to power 1, 0, 1, 2, 3, 4, 5. 2 raised to power 5, 32. So we're gonna remove 1 from it. So when we remove 1 from it, we get 31. And the binary representation is easy. We just gonna remove this one, and all the bits after this one are gonna turn to 1. And then we do the AND operation. So we do the AND operation, we get 0, 0, 0, 0, 0, and 0. Okay, so this is this one. And sorry, this one, the earlier one, it's not actually this. It's actually this first iteration. So this was first iteration and this is the second iteration. In the second iteration we get all the bits as zeros. So we do nothing. Fine. Now I think It's easy for you to write the code, but let me help you there also. So I'm going to write a function which is going to return an integer value, right? I'm going to name that function count. It's going to take integer n as a value. After that, I'm going to maintain a variable int res, similar to the naive solution, and I'm going to initialize it to 0. I'm going to run a while loop. So tell me, until when this loop will run? It will run when the number becomes 0, right? Until the number becomes 0, it will run. So while n is not equal to 0, or I can say n is greater than 0, I will run this loop. Now, the n's value will keep on updating itself, right? First, the initial value was this, then it changed to this, and then it changed to this ultimately. So the n's value is going to change, and what is it going to change to? So first, what we need to do is we need to find this n minus one, right? This n minus one number. So we simply do n minus one. So when we do n minus one, we get this number, right? And add operation with the initial number. So there is an add operation with the initial number. This will give us this number, the first iteration one number. And if we are inside the loop, we need to update the value of this res. Okay. Then we return the res at last. Okay. We have already written the solution here, but let's see how the solution actually works. Let's observe. So basically what we did was, we first of all found a number which is one less to the initial number. So if you observe carefully, all the bits except the last bits flipped to 1 and the last bit flipped to 0. We took the advantage of this. We knew that all these zeros are not going to matter when we take add operation, because it's ultimately going to get 0 only, right? These flipped bits are not going to matter to us, because ultimately when we do add operation with the above the initial number, it's going to turn out to be 0 only. Our main purpose of flip or of subtracting one was to delete this last one, and we actually deleted it. Look, this one changed to 0. So we got a, in the response we removed the 0 when we did the add operation, and we repeated it. We kept on repeating until our number became 0. So out of this keen observation, we wrote that code down. Now this is not the best approach. This is more optimized than the naive approach. Next, we are going to look at a lookup table method, which takes constant time to find number of set bits.